So we've got our multidimensional Black-Scholes equation, and we've got the solution to that multidimensional Black-Scholes equation, which has the payoff in it. Let's try this out with our example. So that example basket option we were talking about, it's a weird option where if there's, it depends on three stocks. If stock 3 is less than 30, then I can exercise that option. And if I exercise that option at expiry, so it's a European option, I get to buy stock 1 for $10 and at the exact same time sell stock 2 for $20. So it's got a little bit of a call flavor in it and a little bit of a put flavor in it. And we looked at scenarios where even though I might lose some money on either the call part or the put part, I'll make more money on the other part. So sometimes it's advantageous to do it if I'm allowed to. And we had looked at sort of the region here. So this, I want to be on the purple side of these planes. So this is the stock 3 is equal to 30. So below that is when I'm allowed to do it. And on this side of this plane here, on the purple side, is where I would make money. So in this region is where I'm allowed to and where I would want to, the intersection of where I'm allowed to and where I would want to. So this is sort of the interval. Now let's set up our answer here for our specific scenario. So we need the risk-free rate of return. Where would we get that? Now I'm just putting these numbers in. This is just a fictitious fun example, but where would I actually get the risk-free rate of return? 28-day T-bill rate would be an example of where I could get that. What about the volatilities of the three stocks? Well, you could take the standard deviation of the returns, the annualized standard deviation of the returns. What about these correlations? Now this is new because things are, the option depends on multiple stocks. It's a basket option. So here's our correlation matrix. I know that it has ones down the diagonal because that's how stock 1 is correlated to stock 1. Stock 2 correlated to stock 2, stock 3 correlated to stock 3. Our correlation with stock 1 and stock 2 is 0.3. And here I've got a negative correlation with 1, and so when one stock goes up, the other one tends to go down. So they're kind of balanced. We know that this correlation matrix is symmetric. And so, and we got to talk about where we would get these numbers. We would get these by comparing we'd have the two returns, the return for stock 1 and the return for stock 2, and get the correlation between those for a specific time period. So now I've got my correlation matrix, which I need to go in here. I need its inverse, and I'm going to need its determinant to go in our formula that we derived last time. What else do we need? Well, let's get this alpha. So in our case, our alphas are going to be a three-dimensional vector. So it's going to be alpha 1 is going to be the ln of stock 1, the ln of y1. Okay, so the y's are the variables that I integrate over, that I sum over. So when I'm finished my triple integral in this case, there won't be any y's. R sigma 1 is 0.4. And t minus t. So the option expires in a quarter of a year. So our t minus t here is a quarter of a year. and our sigma 1 is 0.4. So we don't have an S in here. We don't know what the stock values are right now. Let's get the other alphas. So stock 2, Y2, stock 3, Y3, and now the R's stay the same. The volatilities are different though. 0.2 and 0.2. Oh, I don't like this. I'm forgetting I don't have my square root of 0.25 here. So I'm filling in the volatilities for this, 0.2, 0.2, that stays the same. The next volatility is 0.3, 0.3, 0.3. So then I can make my alpha vector. Okay, so do I have all the pieces that I need then to do this triple integral? I'm going to need to build this front piece here. This e to the, this will have the y's in it. Our payoffs will also have the y in it. Let's build this integral. Well, you know, we're trying to build this. Let's build this front piece first. So there's our discount. And n is going to be 3 because there's 3 stocks in here. The time left is a quarter of a year. 2 pi, we're good with that. I need the determinant of this matrix. I need the determinant of the correlation matrix. So let's get that. Okay, so that determinant is, let's put that up here. Remember, this is symmetric positive definite, so I'm not worried about the determinant being a negative number and me having to take the square root of a negative number. And now the product of all the sigmas. So that's going to be 0.4 times 0.2 times 0.3. Okay, so this is our front, the constant that's in front of that triple integral. Let's just get a number for it. All right, so we're still building this whole thing here. We've got the front matter. Let's worry about this piece here now. So that front stuff simplifies to be the 22 and change. Now I've got three, we're integrating over three y's, so it's a triple integral. Y1, y2, y3. Okay, I had to put this payoff, and we got to worry about these endpoints now. And there's this piece up here, this e to the. So let's see what this is. I'm going to need the inverse. I'm going to need the inverse of the correlation matrix. Let's go up here, get the inverse of this matrix. All right, okay, so this, I mean, there's a lot of calculations here. When we did the single example, there was a lot. We're just setting up the integral. I need these alphas as vectors, and I'm going to multiply those. So this alpha needs to be a column vector, and here it's a row vector. So when I multiply this out, I get one piece in here, and it'll have y's in it. So let's turn this into, let's get ready to put a column vector in there. Right, yeah. So I need this. This is the row vector. Let's take this as the row vector. Here's the transpose row vector, and I need, okay, I'm gonna have to make this small for a second just so I can fit everything in. Okay, so yeah, that's huge. Let's clean this up. When we tidy this up, it should end up to be, we got a 3 by 3, a 3 by 1, a 1 by 3. This will end up being a 1 by 3 piece. Let's simplify this. Oh yeah, so simple. But, all right. That's, okay, we can't see it because it's too small, but this has S1, S2, S3 in it. They're constants with respect to the integral, and it's got y's in it, and those are the variables over which I integrate, and it goes like crazy long here, but it's a function with, basically think of it as it's got y1s and y2s and y3s in it. We got to integrate over that. So in order to sort of represent this, I'm going to do it this way. This equals, and it's a function of, it's got y1, it's got y1, y2, y3 in it. And those are the functions over which I'm going to integrate. And it's also got the S1, S2, S3, and those are, with respect to the integration, constants. I'm going to just call that like h for a function of. So I have a piece of algebra that isn't like 3 miles long. All right. If we had s values, it would make this a little bit smaller. So let's go back and put in what the s's are. So I'm going to go and take readings on what the actual stock values are now. So, and by take readings, I mean like just make up for our example. S1 is going to be equal to $11. S2 is going to be equal to $19, and S3 is going to be equal to $28. So right now, I mean, in a quarter of a year, it might have risen above it. I'm not allowed, but these are the values that we have now. So we can simplify some of these A's and stuff. Okay, so to finish this example, I picked stock values. So we would look these up, current stock values, let's say stock one $11, stock two $19, stock three $28. That's going to put numbers in here, and these things will simplify smaller and fit on the screen, basically. So I went back to where we were expanding this alpha transpose, the inverse of sigma correlation matrix alpha here, and I put in the values and simplified it down. And instead of this, okay, we're at. I'm gonna make it bigger in a second here, but I mean this goes way off the screen. I can't fit that. But when I put the values in, it simplifies down to something that's, well, at least can fit on the screen. But it's still got y1s, y2s, and y3s in it. So that's going to go up here. So before we put that up here, then we got to worry about the rest is already in the interval, right? Or integral. This 1 over y1, y2, y3, that's fine. The dy, that's good. We got to get the payoff. So our payoff only has y1, y2, y3 in it. Now, the payoff doesn't depend on y3. We're only allowed to be in. So let's put our payoff in here. How much do we get at the end? So all the way up to here, we get to buy. So it's like a call for S1. So our value would be E minus S1, 10 minus S1. Let's put our payoff in here. So this would be 10 minus S1 plus, so this is if we exercise it, so it's a max of 0 or this. If we exercise it, we get to sell S2 for $20, so it's like a put. So 20 minus S2. So when we clean this up, this 10 minus S1 is not good. It's S1 minus 10. Duh. Because it's like a call. Right? If we get to buy stock one for $20 or for $15, let's say that piece is worth. So let's for $5. Let's clean that up. That's going to be S1 minus S2. S1 minus S2 plus $10. So the payoff is going to be the max of that or 0. Okay, but 1 minus 2 plus 10. That's what I want back down here for this payoff. So this piece is going to be y1, because remember we write the payoffs in terms of the y's, the function we're going to integrate out, minus y2 plus 10. That's what we get if we're allowed to exercise the option. Okay, let's go back to this piece here. So I want to be underneath this. I want to be underneath this for z, the y3 part, and that s1 minus s2 plus 10. That's this purple plane here. Let's set up our. Okay, we just this piece here. I have. It's all this mess that I haven't put in yet because it's going to make it huge. But let's do these endpoints on the integrals. That's going to be our first thing. So for we're doing y1 first. So let's go back here. This is going to be actually the thing from multivariable calculus that we got to remember. So I'm integrating the x, and then the y, and then the z. The z's going to be easy. The y3 is going to be easy. It's just 0 to 30. It's the x and the y piece. So x is going from x equals 0. Let's do the y first, because I think the y is going to be easier. The y is going from y equals 0 to this plane, which I should write as y equals. This plane is the dividing line between, on the purple side, when the option should be exercised, I want to exercise it because I make money, and the red side of that plane, don't exercise it even if I could, because I would lose money. So this plane, that's where the payoff is equal to 0. So the y's, I'm going to do y2 first, then y1. y2 goes from 0 to that plane, and that plane is equal to y2 equals y1 plus 10. So this 0 here is y2 equals 0, where I start, and this is the y2 equals y1 plus 10. So let's go back and look. That's me integrating from y equals 0, y2 equals 0 to y2 equals y1 plus 10. Now, I did y2 first because x goes from, in this shape, it goes to infinity. So x2 is going from 0 to infinity, and y3 is going from 0 to 30. The shape, the volume over which I'm summing up that triple integral is underneath this purple piece here. And now I've made the triple integral. Well, the only thing, to finish this, I got to put all of this mess here with the y1s, y2s, and y3s in here. This won't be worth it because now you waited. I'm going to put it in here and it's just a big mess. All right, so this is the integral that we have to integrate in order to get the value of that option at that particular stock price. We sum it up over. And yeah, let's see. Yeah, it's a there it is. It's a mess. How are we going to integrate that? Well, I don't want to do it actual analytical pencil and paper. Let's do it Monte Carlo. Let's do Monte Carlo integration to solve this integral.